All right, you guys. So we've gone over Bohr models a lot. We've used them quite a bit, and they're a great way to visualize everything about an atom, a specific atom. The particles in the nucleus, the number of electron shells that the electrons are on, the total number of electrons, all that good stuff. But it turns out that they're a little too cumbersome to use for some of our purposes moving forward. We're going to be using a different kind of model, an electron dot diagram. You can also heard them called Lewis dot diagrams or just Lewis diagrams, all the same thing. These are much more handy when we're trying to figure out what kinds of compounds things are going to form, how the electrons are going to move, that kind of stuff. Okay, so here's some of what these look like. There's hydrogen, carbon, boron, oxygen. Right, so they're a whole lot simpler, which makes them really, really handy to use for certain applications. So let's take a look at how you do these. So the nucleus is just represented by the atomic symbol. You just use the one or two letter symbol straight off the periodic table. Just remember, if it's a two-letter symbol, first one's capitalized, second one is not. If it's a one-letter symbol, it's always capitalized. Okay, so that's our nucleus. To determine the number of valence electrons, and you do this by looking at the group, the column that your element is in on the periodic table. Group number one has one valence electron, two has two, skip the um, transition metals, 13 has three, and so on, right? You're going to draw the valence electrons as dots around the chemical symbol. Okay, fill out one side at a time before you pair the electrons up. So let's do an example. Nitrogen. Okay, so we got nitrogen here. If we imagine nitrogen with like a box around it, so imagine a box that got four sides, right? Those are the sides we're going to fill with electrons. Now, if we look on the periodic table, nitrogen's in group 15, so it's got five valence electrons. Okay, so we're going to put these around nitrogen. Okay, so you put one on each side, right? We don't pair them until we have to, all right? And I've still got one valence electron, means I need to pair it. So I'll do it right there. Okay, now which side I pair up doesn't matter. Um, just that you don't pair them until you have to. Okay, so that is a Lewis dot structure or electron dot structure of nitrogen, just like that. Okay, all right. So a little practice time for you. Try and draw these. Remember, you're gonna need your periodic table. Um, Follow that step by step. One, draw the chemical symbol in there, then put the valence electrons around it. Okay. All right. So let's look at hydrogen here. Hydrogen has one valence electron. It's capital H. Where you put that one valence electron, it could go on any of those four sides. Doesn't matter. That's correct. Okay. Carbon. Carbon has four valence electrons. So carbon must look just like this. None of those should be paired up because remember you don't pair them until you have to. So four isn't enough to pair any side. Fluorine, it's got seven valence electrons. Only got one spot to get full, right? Phosphorus is in group 15. So it's got five valence electrons. So one, two, three, four. Then you got to pair one up. So we got a paired one there as well. All right. So that's the basics of just making these electron dot structures. Now, what can we do with these things? Yeah, so what can we do with these things? So we can use them to show bond formation and to predict what kinds of bonds are going to form. Okay. So if you know two elements and you want to see how they're going to combine, you're going to draw the electron dot structures of the elements, transfer electrons from the metal to the nonmetal. Because remember, metals want to give up electrons to become stable. Nonmetals want to accept electrons to become stable. And then add elements as needed. So you're trying to get all the electrons off of the metal and fill up the energy levels of the nonmetals. And filling it up means 8 around the nonmetal, right? Because of that octet rule. Okay, so you continue transferring until all atoms are stable. So you want all the metal atoms to have given up all their valence electrons, and all the nonmetals to have filled up their energy levels, their valence shell, with 8. Okay, then you can write the chemical formula using subscripts to show how many of each element are needed. Okay, so when I ask you to do these, when I give you 2 elements and tell me how they're going to bond, what compound they're going to form, use this step-by-step process. Now, it might not make a whole lot of sense right now, but we'll do some examples. Okay. So, what compound is going to form between sodium and chlorine? We've seen this before, and this is an easy example. So first, I draw my electron dot structures. Sodium's in group 1. It's got 1 valence electron. Boom, there's my electron dot structure for sodium. Chlorine, group 17. Boom, got 7 valence electrons. Now, this sodium wants to give up an electron. Chlorine really wants to gain one, so it'll fill up that valence shell. So boom, the sodium gives one up. Now this sodium electron's over here. Chlorine's happy because its valence electron shells is full. Sodium's happy because it gave up its valence electrons. Okay, so you only need one of each to make that happen. And the formula is going to be NaCl. So 1 sodium atom with 1 chloride atom makes your sodium chloride, also known as table salt. So let's check out another example. Example number 2, aluminum and chlorine. Okay, so our aluminum is in group 13. Its electron dot structure is going to look something like that. Okay. Now again, when you draw it, what sides you put these 3 on doesn't matter as long as they're not paired up. Okay. So aluminum has 3 to give. Chlorine has 7 valence electrons. So chlorine just wants 1 electron, and it'll be happy and stable. But aluminum has 3 to give, so what happens? Okay, so aluminum gives 1 to this chlorine. That's chlorine's happy. It's not going to take any more. So what do we do with these other 2 aluminums? Well, we've got to add more chlorines to take them. Okay, so it takes 3 chlorines reacting with 1 aluminum to make a happy, stable compound. Boom. And this is how you would write that chemical formula. Al for aluminum, chlorine, you need 3 of them, so you put the 3 down here. So with the subscripts, this is telling you how many of this element there are. If it was up here, it'd be a charge, so you want to make sure and put it down here. And we know it'll take 3 chlorines to make this compound because each one will only accept 1 electron. So you need 3 of them to make this aluminum happy and take all 3 of those electrons. Okay, so a little bit of practice. And let's look at these one at a time here. Okay, so potassium and chlorine. Potassium's in group 1. It's got 1 valence electron. Chlorine's in group 17. It needs 1. So real easy, just like sodium chloride. Boom, you get potassium chloride. Magnesium and fluorine. Magnesium has 2 to go up. Fluorine can only take 1. So boom, boom, it takes 2 fluorine with 1 magnesium. There's your magnesium fluoride. Aluminum and nitrogen. So aluminum has 3 valence. Nitrogen has 5. So nitrogen wants 3 electrons. Aluminum wants to give 3, so it only takes 1 of each. Aluminum nitride there. Okay. The last one, magnesium phosphorus. Okay, so this one took a little doing. Okay, so you got magnesium, has 2 valence electrons, wants to get rid of those. Phosphorus needs 3 to be happy and stable. So boom, boom, takes 2, but phosphorus isn't happy yet. This magnesium's happy, but phosphorus is not, so we need more electrons. Okay, this magnesium can give it 1. Now this phosphorus is happy, but the magnesium still has 1 to give. Okay, boom. Now these 2 magnesiums are good, but the phosphorus still needs a couple. So we need 1 more magnesium to fill that up. And that gives us magnesium 3 phosphate. Okay. So as you're doing this, just keep moving electrons and adding elements as needed until it all balances out and you get everything stable and happy. The metal's given all the electrons it has up. The non-metal has filled up its valence shell. Okay. All right.